Hello, Math 140 students. This is your instructor, Cindy Enrique, and we are back for section 11.6. So we are going to go over log and exponential equations and applications. So we are going to solve our log equations. So the first thing we want to do is make sure that the log is isolated. We have a single log that's isolated, which is perfect. So all we have to do now is to make sure that we rewrite it in exponential form. So we have our base, that's 3, and we also have our exponent, that's 1. So what I have is I have 3 to the 1 power is equal to 2x plus 5. So really 3 to the 1 power is just 3, so I have 2x plus 5. So I am going to subtract 5 from both sides. So now I have my 3 minus 5, which is going to give me a negative 2 is equal to 2x. So divide by 2, divide by 2, I'm going to get that negative 1 is equal to x. So negative 1 is equal to x. And remember, before you box your answer, you want to check it in your original solution. So if I were to plug up bring up my calculator, I'm going to plug that in. What if I had log parentheses and I had my 2 parentheses, and what was it again? It was negative 1 plus 5. And notice how this is log base 3, but I don't have that. I just want to make sure that the inside won't be negative. It's not negative, it's a small decimal number. So I definitely know that my answer is x is equal to negative 1. For number 2, what's different about this one is that I have log in 2 places. So logs on both sides of equation. So what I want to do is I want to combine all the logs to one side. So that means I'm going to add this log base 4 x minus 3 to both sides. So then this side, it will cancel. So I'll be left with log base 4 of x plus log base 4 of x minus 3 is equal to 1. Now I have logs on one side of my equation. Now that I'm here, I have addition. So using my properties of logs, that means I'm going to combine them into multiplication. So I have log base 4. Now I'm going to multiply. So I have x that's going to get multiplied by that x minus 3. And all of this is equal to 1. So I'm going to go ahead and distribute here. When I distribute, I'm going to have an x squared minus 3x. Now that I'm here, I have distributed the x on the inside. I have a single log by itself. It's condensed. So now at this point, what I want to do is rewrite it in exponential. So to rewrite it as an exponential, I have 4 as my base. My exponent is 1. So it's equal to x squared minus 3x. The reason, or because I have a degree 2, that means I'm going to set my equation equal to 0. So I'm going to have minus 4 minus 4. So that 0 is equal to x squared minus 3x minus 4. So then from here, I can go ahead and factor. So I'm going to have 4 and 1, negative 4 and a positive 1. That is how that's going to factor. So 0 is equal to x minus 4 and my x plus 1. That gives me a negative 3, and when I multiply, a negative 4. So I have x minus 4 is equal to 0. So x is equal to a positive 4. x plus 1 is equal to 0. So x is equal to a negative 1. And remember, you cannot have a negative inside your log. So when I plug that one in, it will give me an error. So the only possible answer that I have is that x is equal to 4. Okay? Now, for example number 2, I'm looking at this and I'm like, okay, well, I have a single log. When I have a log of x and there isn't a base, the base defaults to be base 10. Base defaults to 10. So this is really a base 10 here. So when I rewrite it, I have log base 10 of x plus 300 is equal to a 3.7. So now I'm going to rewrite it as an exponential. So I have 10 to the 3.7 is equal to x plus 300. So I'm going to go ahead and subtract 300 from both sides. So I can get x, oops, not x, but 10 to the 3.7 minus 300 is equal to x. I'm just going to rewrite that. X is equal to 10 to the 3.7 minus 300. And this is my exact answer. So on your new end, it might ask you to write this as a decimal. I actually don't know what this is going to look like, so I might as well just go ahead and write it. So let's see, let's bring that calculator up. So I have this as 10 to the power of 3.7. I have minus 300. And so I have this number, and usually, rule of thumb, go to the 4 decimal places. So the 4th digit here is 3, and the 5th digit is 3. So that tells me to round down, so to leave it alone. So my final answer, if I want the decimal approximation, x is equal to 4711.8723. Okay? For example number 4, it's very similar. Here, because I have the addition, that tells us that we are going to be multiplying those insides together. So we have ln, and it's equal to the ln of that 9x minus 17. So this is where the magic happens. This x plus 2 is going to get multiplied. And it's going to get multiplied by that x minus 1. So I'm going to go ahead and FOIL this out. So I'm going to have my ln, and I'm going to have this as an x squared minus x plus x minus 1 is equal to my ln of 9x minus 17. So the nice thing about this is that the negative x and the positive x cancels out, so you're just left with an x squared minus 1. And it's equal to the ln of the 9x minus 17. And since you have ln on both sides, you can think about it as doing e to both sides, so it can cancel. So then that way you will be left with the x squared minus 1 is equal to 9x minus 17. And since it's a degree 2 or exponent of 2, I'm going to set everything to equal to 0. So I'm going to subtract 9x from both sides. I'm going to add 17 to both sides. And I kind of ran out of room, so I'm going to write it over here. So I'll have my x squared minus 9x minus 1 plus 17 equal to 0. So that will give me x squared minus 9x plus 16 equal to 0. So I'm going to go ahead and factor that. So let's think about 16. I have 1 times 16, 2 times 8, and 4 times 4 is 16. So is there any way to get a 9? I don't think there is. So I tried to factor, but it's not going to factor. So it's like, okay, I gave that a try. So if it can't be factored, then what you do is you do the quadratic formula. So can't factor. Try the quadratic formula. Which is your negative b plus or minus the square root of b squared minus 4ac all over my 2a. So here my a would be 1, my b is negative 9, and my c is positive 16. So I would have this as a negative 9 plus or minus, and I'm going to have my b squared. So that would be my negative 9 squared minus 4 times my a, which is 1, times my c, which is 16, so we'll get a positive 17. And then I have my 2 on the bottom. So I have that x is equal to 9 plus or minus the square root of 17, all divided by 2, as my final answer. Okay, so that is what happens when you can't factor. If it can't factor, I tried, I even did it off to the side, like, okay, well, you know, well, actually, it's not 1 times 6, it's 1 times 16. That's what I was trying to do. But 2 times 8 is 16, 4 times 4 is 16, and those are the only factors of 16. And none of them were going to add up to give me 9. And so, can't factor, so I had to go to the next best, which would be the quadratic formula. All right, so for example number 5, it says to solve this. Well, we can think about it as, well, look at our base 4. Can we rewrite it so that 64 has a base of 4? Well, let's think about this. I have 4 to the 1 power, which is 4. 4 squared, which is 16. 4 to the 3rd power is going to give me 64. So I can rewrite that 64 as 4 to the 3rd power. So I have 4 to the 2x minus 9 is equal to, now I can rewrite that 64 as 4 to the 3rd power. 64 is the same as 4 times 4 times 4, which is 64. So now that I have the same base, then that means that the exponents would have to be the same. So here, I'm going to set the exponents equal to each other. So I can have 2x minus 9 is going to be equal to my positive 3. So plus 9 on both sides. So now I have 2x is equal to, and I have 9 plus 3, which is my 12. From here, divide by 2, divide by 2. So I can get that x is equal to my positive 6. So 4 to the 2 times 6 minus 9 is equal to 64. Okay. Now we have some more examples. So now I have 2 to the x times x plus 3 is equal to the 1/4. And I'm like, okay, well, this is a bit more tricky. It's still doable. I know my rules of exponents. I know if I have x to the m to the n power, then I would rewrite it as x to the m times n. So it would be multiplication. So that's what I'm going to do here with this x. I'm going to multiply this x because that is my rules of exponents. So I'm going to have 2. And now I'm multiplying x times x is x squared, and x times 3 is a positive 3x. And I have this equal to a positive 1/4. And again, I'm going to try to see if I can rewrite that 1/4 into something else. Well, I'm going to do this over to the side. I know that 2 to the 1 is equal to 2, and 2 squared is equal to 4. So the only way to get the reciprocal of that is if I were to write it as a negative exponent. So 2 to the negative 1 is a 1/2, and 2 to the negative 2 is a 1/4. So now I can rewrite that 2 to the negative 2 as a 1/4. So that 1/4 is going to change. So I still have this as 2x squared plus 3x. But now, since I'm switching that 1/4, I know that 1/4 is really just 2 to the negative 2 power. So the beautiful thing about this is that now I have the same base, so now my exponents are going to be set equal to each other. So that x squared plus 3x is equal to the exponent of negative 2. So I'm going to add 2 to both sides so that I can get x squared plus 3x plus 2 is equal to 0. So 2 times 1 is 2, and 2 plus 1 is 3. So x plus 2 is equal to 0. So x is equal to negative 2. X plus 1 is equal to 0. So x is equal to a negative 1. So I'm going to go ahead and plug this into my calculator and see what I end up getting here. So let's see. I'm going to have, maybe I need to stroll this up a little bit more taller. Okay. All right, so I'm going to have, oops, let's parentheses. And I have 2 to the power of, let's try negative 2 first. So negative 2. Then I'm going to close the parentheses to the power of negative 2 plus 3. We are hoping that that's going to give me my 1/4. If it is, then I know my answer is going to be true at negative 2. And it's 0.25, and just to make sure, that is exactly 1/4. So this is a good answer. I have checked it in my original solution. Now let's try it for negative 1. So now I'm going to have parentheses, negative 2 to the power of negative 1 to the power of negative 1 plus 3. And I can see that I accidentally put a negative sign in there. Okay, so 2 to the negative 1 to the power of negative 1 plus 3. That should give me that 1/4 or that 0.25. And it does. And remember that 0.25 is the same as my 1/4. So both of those answers were good. So x is equal to negative 2 and x is equal to negative 1 were fantastic answers to have. Now for number 7, this one's slightly different. This one is different because there's no way I can make 32 look like a base of 5, right? We have 5 times 1, and I'll even write it, right? 5 times 1 is 5. 5 squared is 25. 5 to the third power, that's 125. So 32 doesn't work when I have a power or a base of 5. There's no power of 5 that would give me a 32 or 1/32. So I'm going to have to rely on something else. Instead, I'm going to log both sides. So I'm going to say log, and I have my 5 to the x is equal to log, and I have my 32. So I literally write log in front of both those equations. Now, with my rule, I know that I can take that x out with my power rule. So x times log of 5 is equal to my log of 32. And since this is together by multiplication, what's the opposite of multiplication? Division. So I'm going to divide by log of 5. So divide by log of 5. Now I can get the x isolated. I have log of 32 divided by log of 5. So this would be my exact answer. I could also get the decimal approximation. I would just need to plug that into my calculator. So I would have my fraction. So it would be log of 32 over my log of 5. So log of 32 divided by log of 5. And so I have my answer. And so notice that's a very big decimal. So I'm going to round to the 4 decimal places. So I have 1, 5, 3, 3, 8. So that 8 is that 5th decimal. It tells me what to do with the 4th. Since it's 5 or bigger, that tells me to round up. So it should be 2.1534. So I'm going to go ahead and write that down. So the decimal approximation, I should have that x is approximately 2.1534. Okay. For example number 8, here I have t as my variable. So t is variable to solve for. A lot of people see this and it's like, oh, we have to find the value of e. No, e is a number. E is just like pi. E, remember, if I plug that into my calculator, I actually have a numerical value for this. If I were to plug e into my calculator, I get 2.7128, right? That's almost the exact same thing as pi, where it's never ending, never repeating. So again, e is a value, just like pi. It's irrational. It's non-repeating, non-terminating. So we're going to use that to our advantage. So the only thing we're solving for here is t. So I'm going to subtract 1 from both sides. So I can have e to the negative 0.2t is equal to 7.52. From here, the only way to get rid of e is if I were to ln both sides. So ln the e to the negative 0.2t equal to the ln of that 7.52. And so when I do this, the ln and the e cancel, so you're left with a negative 0.2t is equal to ln of 7.52. And since that negative 0.2 is held by multiplication, to break it, we do the opposite. The opposite of multiplication is division. So now I'm going to have t is equal to the ln of 7.52 divided by a negative 0.2. And that is my exact answer. And of course, I can plug this into my calculator. So in my calculator, I'm going to have my fraction. So that I can have my ln of 7.52. And at the bottom, I have a negative 0.2. And I get that negative 10.0878. So again, rounding to the 4 decimal places. So I can have that the decimal approximation is going to be t, and it's going to be negative 10.0878. Okay. Now we're going to go into our word problem. So it says the population of the world was estimated to reach 6.5 billion in April 2006. The population growth for the world is estimated to be 1.4%. This function, P of t, represents the world population in billions as a function of the number of years after April 2006. Use the function to estimate the world population in April 2010. So here, the numbers of years after 2006, this is your initial year. So your initial year is April of 2006. So then t would give me 0, would correspond to April of 2006. So everything refers back to April 2006. There's no 2005, 2001, 1990, 1980, 1950s, 1920s, 1900s. The first day in this word problem that exists is 2006, April 2006. So everything is going to be in reference to April 2006. So when it says April 2010, well, how many years is that since April 2006? Hopefully you remembered that you're going to do a subtraction. So 2010 minus 2006. And that is going to give me 4. So this is telling me that my t equal to 4 represents my April 2010. So I'm going to plug that into my equation. So I have P of t is equal to my 6.5, 1.014, and that t value here is 4. So I'm going to go ahead and use my calculator for this. So I have my 6, oops, let's clear everything, 6.5 parentheses 1.014 to the power of 4. Okay, so my answer is a 6.871715559. Okay, let's see if it says to do any rounding. Oh, it just says to estimate the world population. So I'm just going to go ahead and estimate it as a 6.87, and it's not 6.87 people, right? That can't be the world population to be almost 7 people, or even thousands, right? Or even hundreds. It's going to be billions. So 6.87 billion people is supposed to be the world population in 2010. Now for part B is slightly different. It says use the function to estimate the amount of time after April 2006 required for the world population to reach 13 billion. So now it's specifically asking me to estimate the amount of time. So what is the variable for time? That's t. So I'm trying to solve for t. And what they're giving me is the world population to be 13 billion. So population is equal to 13 billion. Well, here the population is referred to as P of t. That's equal to a 13. So I have my equation of P of t is equal to my 6.5, 1.014 to the t power. So that 13, I'm going to plug that into my P of t. So I'm going to have 13 equal to my 6.5, 1.014 to the t power. And that is my goal. My goal is to solve for t. Now, rules of operation, rules of order of operations. Can I do my multiplication before I do my exponent? Well, according to PEMDAS, or please excuse my dear Aunt Sally, I would have to do exponents before multiplication, okay? So that means I can't just multiply the 6.5 times the 1.014. Instead, I have to isolate the exponent. So in order to do that, I'm going to divide it out. So I'm going to divide by 6.5 on both sides. So I'm going to have 13 divided by 6.5, and that's going to give me 2. And that's equal to a 1.014 to the t power. So now that I'm here, I'm going to write log on both sides. So log of 2 is equal to log of that 1.014 to the t power. And so now I'm going to use my power rule to bring that t out in front. So I have log of 2 is equal to power rule, t out in front, times my log of 1.014. And since that log and the t is together, it's bounded by multiplication. Well, the opposite of multiplication is division. So divide by log of 1.014. So now my exact answer is going to be that log of 2 over log of 1.014 is equal to t. Okay? And so that's going to be my exact answer. And it does say to estimate, right? It says use the function to estimate the function of time. So you don't say, oh yeah, the time is log 2 divided by log of 1.014. I think maybe the only person in the world that would understand you is a really big math nerd, right? I don't think you were like, oh yeah, I'm log 2 of log of 1.014 years old today. Everybody's gonna be like, what? How old are you? So make sure that you give me the decimal approximation. So we write that on our calculator as a log of 2 divided by my log of 1.014. And I get it at 49.856. So I'm just going to say it's 49.9. Okay, so 49.9. And it is my time, so it's going to be my years. So in about 49.9 years, the world population would be about 13 billion, okay? All right. So we have our next example, example number 10. So this is about half-life. So it says radioactive strontium-90 has a half-life of 28 years. If 100 grams of strontium-90 is initially present, the amount left after t years is approximated by this function, a of t. Find the amount present after 85 years. So here we have our years. So our years is given to you by t. So t is equal to 85. So that is what you're plugging in to your equation. So you have your a of t is equal to your 100 times e to the negative 0.0248, and that t value that you're plugging in is 85. So, busting out the calculator, we have 100, and we have our e value to the negative 0.0248 being multiplied by 85. So it looks like it's 12.14 or 12.15. So 12.15. And it would be G for grams. Okay. Now for part B, it says, how long will it take for the amount of this element to decay to 40 grams? So how long will it take? So you're asking for time. So my time would be blah, 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 blah. but I don't know my time. That's what I'm trying to figure out. So that 40 grams is your final amount. So that's my A of t is equal to 40. So I have my equation, A of t is equal to my 100 times e to the negative 0.0248 t power. But the only thing I'm going to be plugging in here is that 40. So 40 is equal to my 100 e to negative 0.0248 t. So to solve for t, I'm going to divide by 100 so that I have 40 divided by 100, which is a 0.4. Now I'm going to write ln in front of both of them. And because that happens, the LE, remember, they are inverses of each other, so they cancel each other out. So I'm left with an ln of 0.4 is equal to a negative 0.0248 t. So now, since it's together, bounded by multiplication, to break that bond, it would be division. So divide by negative 0.0248. So I have that ln of 0.4 is equal to a negative 0.0248 is equal to my t value. And that would be my exact answer. And of course, if I wanted the decimal approximation, that means just plugging it into my calculator so that I would have my fraction. So it would have my ln of 0.4. And down at the bottom, I have my negative 0.0248. And I get my answer as a 36.94720693. So let's just go ahead with the 36.95. And that would be years. Okay. So I have 36.95 years, more or less. And that is the end of chapter 11. So if you guys have any questions, please feel free to email me or contact the Math Success Center if you guys have any further questions. Thank you.